everyone, in this video I'm sharing a node-based system that generates a curve. Here are some examples of what the system is capable of. So let's start. This is the whole node graph. Here are the inputs. This part generates points. The points node generates the point that represents an origin. The number of points parameter defines the total number of points. Because it is the total number, adjustments are needed. The value is clamped to the 0-1 range for count input and subtract by value of 1 for iterations input. As a result, value 0 generates no points, value 1 generates only origin point, and value of 2 and greater generates origin plus next point. Points are generated with extrude operation, which always extrudes the last vertex. A mesh is required for extrusion, so point is transformed to mesh. The index of the last vertex is computed by taking total point count and subtracting 1 since vertex indices use 0-based numbering. That index is then compared with current index. The result is a Boolean value that represents the selection for extrusion. The new point position is at first the position of previous point. It is not offset during extrusion. I prefer to generate the offset after the new point has been created, so the new point itself can be used as the source of random values. If the offset were generated during extrusion, the random value would be based on the index of the source point rather than the newly generated point. For this reason, a position is offset after extrusion for the last point. So selection is again created in same way as before. This all happens in a loop in repeat zone where the output mesh from one iteration becomes the input mesh for the next iteration. The output from loop is converted from mesh to curve. There is an option to transform the curve type from linear to Bezier and send handle type to auto where result is a smooth curve. And the result is curve. This curve is the output of this node group. Now, this part generates the values used as the position offset. Direction and magnitude are generated. Let's start with direction. There are two modes, directional and one direction. The directional mode means that the offset can be applied along three axes, x, y, and z. The one direction mode means that the offset can be applied along only one axis. The directional mode generates the direction with a spherical coordinate system. This is a function, a node graph, that generates a vector based on a spherical coordinate system. There are multiple settings to choose from. A vector can be created as a unit vector or as a vector in volume. The unit vector is used as direction. Then the polar angle or the z component can be defined. This part has input polar angle. The z component is calculated as the cosine of the polar angle. The sine of the polar angle is the radial distance of the sphere at the z level. This part has input z component, so the z component is already defined. The radial distance is calculated as the square root of 1 minus z squared. Since the z component is equal to the cosine of the polar angle and the cosine squared of the angle plus the sine squared of the angle equals 1, the expression 1 minus z squared is equal to sine squared of the polar angle. Taking the square root gives the radial distance of the unit circle at the z level. Switch nodes determine if the z component and radial distance is returned by defining a polar angle or a z component. The menu switch node itself is not used for switching values because connecting multiple menu switch nodes to the same value creates a conflict. This can be solved by wrapping menu switch node to the group node. However, I prefer just using Boolean value from one menu switch node for each option to then select a value dedicated to that option. The cosine of the azimuth angle produces the x component on a unit circle, and the sine of azimuth angle produces the y component on a unit circle. Both values are then multiplied by the calculated radial distance at the z level. All components are then combined to a vector and the result is a unit vector. When vector option which return a vector in volume is enabled, this vector is then multiplied with defined radius. In this case, unit vector as direction is needed. For direction generation, a uniform distribution is desired. That means that every point on the sphere has the same probability of being generated. Because of that, the z component is generated directly instead of generating the polar angle. If the polar angle were generated, then points would be biased towards the poles. Here, 100,000 points are generated for each method. On the left, the points are generated using the polar angle and the azimuth angle. The distribution here is biased towards the poles. In the middle, the points are generated using the z-component and the azimuth angle. The distribution here is uniform. Also, there is another method for generating vector, and that is generating uniform random value for each component. This generates points in cube. When those vectors are normalized to create a unit vector, then points are biased towards corners of that cube. Therefore, the direction is generated using spherical coordinates where a uniform distributed z-component and an azimuth angle are generated. Now, the z-component and the azimuth angle can be generated simply with random values. However, to get more control on interesting shapes, more things are done here. The z-component input expects a value in range from -1 to 1. The azimuth angle expects an angle in radians, so value from 0 to 2p. There are two modes for defining the z parameter. The mode is selected using an index. The index of 0 represents the random mode and the index of 1 represents the sequence mode. The values are defined in the range from 0 to 1, where 0 represents an angle of 0 degrees and 1 represents an angle of 180 degrees between z-axis and the vector. Defining the angle feels more intuitive to me than defining the z-component directly. To get the z-component, the defined angle is multiplied by the value of p because the angle needs to be converted to radians, and the cosine of the angle calculates the z-component. In random mode, the minimum and maximum values define the range for the random value node. The seed is the defined value added by an integer value to maintain a different seed for each random value node. In sequence mode, the generated values are in sequence. This is achieved using a modulo operation. The vertex index is divided by a defined value and the remainder is used as a sequence index. For each sequence index, value is defined. The azimuth angle also supports two modes, 0 random and 1 sequence. Values are defined in the 0-1 range where 0 represents an angle of 0 and 1 represents full circle, 360 degrees. The value is multiplied by 2p to transform angle from normalized values to radians. In the one direction mode, a different approach is used. One of the three axes is selected. There are two modes for this, random and sequence. The index each node then select axis based on the index. For each axis, only two directions are possible, the positive direction and the negative direction along the axis. The selected direction is then combined into a vector where the component corresponding to the selected axis receives that defined value, while the remaining components are set to 0. The direction can be selected using several modes. There are 4 modes, random, only positive, only negative and sequence. A mode can be defined for each axis, which is why the mode input is represented as a vector. The result of this section is the direction. Then there are another two modes, global vector and local vector. The global vector mode outputs the direction directly. The direction defines the offset direction in the global space, which is the object space. The local vector mode outputs the direction defined in the local space of each point. To get the local vector in the global space, it needs to be transformed. There are different ways how local space can be defined. Here are two modes for this. The mode with index 0 is using rotation to define space, where local z-axis is aligned with vector. Align rotation to vector node is used. Rotation is then combined with other transformations to create transformation matrix, and vector is then transformed. The mode with index 1 defines space in a way where direction of previous point as unit vector is local z-axis. The local z-axis and the global z-axis are used as inputs to a cross product operation which produces a vector perpendicular to both of them. Then this vector is normalized and represents the local y-axis. The local z and local y-axis are then used in a cross product operation which produces a vector perpendicular to both of them. The result is normalized and represents the x-axis. Two cases also need to be handled, when the vector is 0, 0, 1 and when it is 0, 0, minus 1. In these cases, the cross product of each of these vectors and the global z-axis becomes the 0 vector. So, if vector is 0, 0, 1, then the space is as if global, not change, and if vector is 0, 0, minus 1, x and z-axis are inverted. So basis is this for vector 0, 0, 1 and this for vector 0, 0, minus 1. The result is a set of basis vectors. To transform vector based on this basis, Each component is multiplied by its corresponding basis vector and the resulting vectors are added together. To visualize that, this is a global space, this is a local space that is right now not transformed, and this is a vector that determines how space is transformed. Right now the vector is 0, 0, 1. Now vector is changed to 1, 1, 1. Mod 0 is currently selected, so the rotation-based approach is being used. This is the result. The space is rotated and vector defines the local z-axis. Now mod 1 is selected and this is the result. Local z-axis is vector, y-axis is perpendicular to global z-axis and local z-axis. It is always on global horizontal plane. X-axis is perpendicular on local z and y-axis. It is as if first the space is rotated around the global z-axis until the local x-axis aligns with the horizontal projection of the vector. The space is then rotated around the local y-axis until the local z-axis aligns with the vector. The transformation is not applied to point 1 since the previous point 0 does not have a direction, therefore point 1 is generated in global space. To get the direction at the previous point, position of previous point is sampled and subtracted by position of point before it. The vector is then normalized to get the unit vector representing the direction. Then there is another option called reflection. The angle between the local z-axis and the vector can range from 0 to 180 degrees. This can produce results where angle becomes greater than desired. If it is not desired, the mode can be changed to local vector and set the polar angle to desired value. However, when generating points in global space, the z-axis points always in one direction, volt z-axis, so this does not work. The way to solve this is to reflect this vector if angle is bigger than 90 degrees. The dot product of the generated direction and the direction at the previous point returns a scalar value. If it is positive, the angle is less than 90 degrees, so the vectors point in the same general direction. If it is 0, the angle is 90 degrees, so the vectors are perpendicular. And if it is negative, the angle is greater than 90 degrees, so the vectors point in the opposite general direction. So value is compared with 0, and if it is less than 0, then vector is reflected. This is the formula for reflection of vector across local horizontal plane. Here, the normal of the reflecting plane is the direction of the previous point. The reflected vector equals the input vector minus twice the dot product of the input vector and the plane normal multiplied by the plane normal. The point with index 0 is not reflected because the first point with index 0 has no direction. To visualize what is happening, here is an example. This is a vector with a magnitude and a direction labeled as vector 0. The reflecting plane is perpendicular to the vector, so the direction of vector 0 as a unit vector represents the normal of this plane. The next vector labeled as vector 1 is generated with a spherical coordinate system. There is menu switch to select if the vector is generated in global or local space. This value is an angle in degrees and represents the polar angle. Now vector 1 is generated in local space and the angle is set to 0. The vector is aligned with the plane normal and with vector 0. Now the angle is increasing to 360 degrees and this is the result. It is the angle between vector 0 and vector 1. So the angle between vector 0 and vector 1 can be controlled. Now vector 1 is generated in global space and angle is set to 0. The vector is aligned with the global z-axis. Now the angle is increasing to 360 degrees and this is the result. It is the angle between the global z-axis and vector 1. So the angle between the vector 0 and the vector 1 cannot be directly controlled. So there is an option to reflect this vector across the reflecting plane and this is the result. When generating the curve as mentioned, it is reflected only when angle between two vectors is greater than 90 degrees. After this, the result is the direction as a unit vector. Then the magnitude is generated with random value node. Min and max values are defined as the vectors to have control over each axis. When the same value is used for all axes, the magnitude between points equals that value. If different values are used, the resulting magnitude depends on the generated direction. As mentioned before, this provides control over each axis and therefore over the overall shape. Seed is added by value 100. Direction is multiplied by magnitude and result goes to offset input in set position node. Here are some examples and the settings used to generate them. Thank you for watching and I wish you the best on your journey.